So as Heike said, I'm a new director at the Max Planck Institute for Astronomy in Heidelberg. I'll say two sentences of advertisement about the department. It's all things exoplanet atmosphere characterization. So that includes observation, theory, instrumentation, and hopefully lab experiments soon as well. And at the moment, we're still pretty small. There's about 9 of us, but I have job ads out this year. So if you're on the market, please go check the AAS job register and check those out. Okay, so today I'll be talking about planets as places. More than any other astronomical object, planets are really places that we can imagine. We can imagine traveling there, even if we can't actually do that. And we're at a very exciting moment in that we've started to begin to characterize what these planets are like. And over the next decade, we'll vastly expand our capability to learn about these planets. So in my talk, I'll focus a little bit on what we know at the moment and where we're going in the future. So all of you guys know this, that exoplanets are much more diverse than the solar system. Here's the familiar plot of planet mass versus distance from the host star. And we know that there are many, many planets on short period orbits, so they're highly irradiated and often tidally locked. There is an abundant population of planets that are intermediate in size between the Earth and Neptune. We're debating at the moment whether these things are truly super Earths or more like mini Neptunes or something in between, something new. We've found many planets that are on the boundary between what we would conventionally call a planet and a star, as well as a whole host of other things. So high eccentricities, planets around 2 stars, planets that are very low density, et cetera, et cetera. And all of this is to say there's a huge region of this parameter space that we've not yet had the sensitivity to explore. So I think we're really just at the beginning of learning what the full diversity of exoplanets looks like. Now that we've found all of these planets, it's a great time to begin characterizing them in more detail. That includes mass measurements, but also detailed study of the atmospheric composition of the planets. And by studying the atmospheres of mature planets today, we can learn a lot about how they formed, how they evolved over time, what their atmospheres are like at the moment, so what their climates are like, what clouds or hazes are present in their atmospheres, how inhomogeneous the planets are. We know that they're 3-dimensional objects, even if we can't resolve that 3D. Well, maybe we can if we're really creative about how we do it. And finally, one of the huge goals of the field is to study the atmospheres of Earth-like planets to infer the possible presence of life. So one slide on how we typically do this. This is relevant for transiting planets, which are the largest number of planets with well-characterized atmospheres. For these systems, when the planet passes in front of its host star, a little bit of the starlight will filter through the planet's atmosphere where it can be absorbed or scattered. And conversely, when the planet passes behind the star, any thermal emission or reflected light from the planet is blocked. And so we can use these techniques to determine the chemical composition of the atmosphere, what the dominant chemical species are, whether clouds or hazes are present, and what the temperature structure of the atmosphere is like. So since this is a relatively short talk, I want to get right into some results. And I'll start first with atmospheric characterization of giant planets, which is particularly interesting because it serves as a fossil record of the formation conditions of the planet. So as the planet is accreting gas and solids from the protoplanetary disk, that is to first order frozen in as the composition of the atmosphere that we see for mature planets today. And in the solar system, there's a well-known trend that less massive planets have higher metallicities, but we only have a sample size of 4. And so exoplanets provide us an opportunity to test whether this is universally true, to better understand how this trend might have arisen and what that means for planet formation. One of the really interesting things about exoplanets is that a lot of them have high temperatures, as I mentioned earlier, and this means that water is well mixed and in the gas phase and easier to see than it is for Jupiter in our own solar system. And so to take advantage of this opportunity, I targeted a particular hot Jupiter, WASP-43b, with the Hubble Space Telescope and measured very precise thermal emission and transmission spectra for the planet. Those are shown on the left. In both cases, there was a strong signature of water absorption in the spectra that I've marked with the horizontal black bar. And based on an atmospheric retrieval of these two spectra, we found that the water volume mixing ratio in the atmosphere has to be between about 200 and 3,000 parts per million. Now, depending on who you're talking to, this may sound more precise or less precise, but the important thing about this is that it's precise enough to put WASP-43b, this hot Jupiter, on the same plot as the solar system planets. And this was 7 years ago now, and we were really surprised to see that this exoplanet, which clearly had a different evolutionary history, it's a hot Jupiter, so it's very close to its star, and yet it followed the solar system trend very well. Moving forward, this measurement inspired a lot of similar work to measure water abundances for a larger sample of exoplanets. And today, this is what the plot looks like. So I think our early result was too good to be true, in the sense that it seemed like we had an exoplanet that matched the solar system exactly. And now when we look at more of them, it appears that there is a very large diversity of atmospheric properties. And one of the most interesting results that is coming out is that a lot of these transiting planets appear to have substellar water abundances. And this is true for planets observed with a wide variety of approaches. So this is true for low resolution spectroscopy coming from Hubble. It's also been seen in high resolution spectroscopy from the ground. It's held true across multiple different analysis approaches. And to be honest, I kind of ignored these results for a while, because any model of planet formation typically predicts that you're accreting a lot of ice-rich planetesimals early in the lifetime of the planet that remain in the atmosphere, so that we would expect water enrichment, not a substellar water abundance. But this is coming up again and again and again, and so I'm highlighting it because I think it's worth thinking about. There haven't been measurements of that many other chemical species. There's some measurements of alkali metals, like particularly sodium, and some measurements of the carbon abundance as well. And those do not appear to be substellar abundances. So it seems like something unusual is going on with the water. And I've just listed as my last bullet point what is going on, because I think we really don't know yet. Perhaps the water really isn't there. Perhaps it's sequestered deeper in the atmosphere than we can see. And fortunately, we have a lot of new data coming soon, which I think will help iron out what's really happening. Here's an example of what a transmission spectrum of a hot Jupiter looks like as measured by the James Webb Space Telescope. So I can finally with certainty say James Webb is expected in 2021. The launch date is December 18th of this year. And the last I heard, the ship that was carrying JWST to the launch site has passed through the Panama Canal. So it looks like we have a green light for launch in just a couple of months. But JWST will be fantastic for exoplanet atmosphere characterization. It has a larger collecting area and a broader wavelength range than Hubble does. So in the simulated spectrum, you can see absorption features from many different species, not only water, but also methane, CO2, and CO. And the expectation is that with data like this, we'll be able to measure the atmospheric metallicity and elemental abundance ratios at least as well as we can for the solar system planets. There are also big developments happening on the ground, and I want to highlight one in particular that I'm involved in, and this is the upgrade to the gravity instrument. So gravity plus is K-band interferometry at the VLT with improved sensitivity relative to the existing gravity instrument. The signal to noise will improve by a factor of 7 or 8. And so here is a simulated spectrum of, oh, I didn't put it on the slide. I think this is HR8799E. And you can see the beautiful CO band head right there at 2.3 microns. And so this will also be really spectacular data. Here's some simulated, some retrieved C to O ratio and metallicity based on this synthetic observation. And you can see that the C to O is constrained to plus or minus 0.02, which is really spectacular. Later in the decade, we'll have results from Ariel, expected in 2028 or so, and this is the first dedicated space mission for exoplanet atmosphere characterization, with the goal of surveying over 500 exoplanet atmospheres. And I think this is going to be really important because as we're seeing, the atmospheric properties of exoplanets are very diverse. And to truly understand what's going on, to have a comprehensive theory of what atmospheres are like, I think we're going to have to divide them up by planet size, by temperature, by host star properties, by orbital period. And so I think a sample of 500 at least is what we need. So that's a big thing to look forward to down the line. We also have really exciting developments for the ELT. Here is a simulated, oh no, it's not a spectrum, this is just the opacity at high resolution, high spectral resolution at the wavelength range accessible with METIS. And you can see that H2O is the dominant opacity source, but if you go to high enough spectral resolution, you can also see absorption lines from HDO, an isotopolog of water. And this is generally true for high spectral resolution, that it allows you to probe species that are lower abundance or less spectrally active than the dominant absorbers. And so this allows you to get a complete chemical census for an exoplanet atmosphere. And not only that, but by measuring the shape and Doppler shift of the absorption lines, you can also constrain the wind speed and atmospheric dynamics of the planet. So lots of things to look forward to over the next decade. Okay, so I want to switch gears now and talk a little bit about smaller planets. A big topic for exoplanets, of course, is what are Earth-like planets like? And unfortunately, those are really, really challenging from an observational standpoint. So I've gotten interested recently in what I'm calling Earth cousins, which are planets that are a little bit bigger or a little bit hotter than the Earth. So starting first with planets that are a little bit bigger, I'm calling these planets Neptuni. Here's the occurrence rate of planets with orbital periods less than 100 days. You can see these two familiar peaks, one centered at approximately the radius of Earth, so terrestrial planets, and another peak centered at about 2.4 times the radius of Earth. It's expected from interior structure models that planets in this radius range would have at least some hydrogen in their atmospheres, maybe 1% or even 0.1%. But they may be very enhanced and volatile species like water, CO2, or methane. And it's very difficult to determine what's actually impossible to determine the interior composition of these planets. Because in this size range, there's a lot of degeneracy between the core mass, the mass of ices, and the mass of gas. And so if we want to learn what these things are made of, we have to study their atmospheres directly. All right, so a big goal is to determine what the atmospheres of these small planets are made out of, but what we have found is that many of them have clouds. This is, again, an older result of mine. For the canonical GJ1214b planet, we used to call it a super Earth. I think we should call it a Neptuno now because we know it has to have at least a little bit of hydrogen. And we observed 15 transits of the planet with Hubble and found that clouds or haze must be present in the atmosphere of the planet because the spectrum is so featureless. It means that there must be a high altitude cloud deck that is blocking transmission of stellar flux. The clouds have to be, yeah, as I said, very high altitude. So the cloud deck pressure is 1/10 of a millibar or lower. Relative to Earth clouds, they're are a couple of hundred millibar. At the equilibrium temperature of the planet, you'd expect condensation from salts and sulfides, or perhaps also photochemical haze formation from methane photolysis by UV photons in the upper atmosphere. But along the theme of exoplanet diversity, after many years of studying these planets, we've found that not all Neptuni have clouds that are so thick we can't see through them. So here's a little snapshot of half a dozen of these planets organized from top to bottom by equilibrium temperature. And you can see that the hotter ones tend to have larger amplitude spectral features. In this case, we're seeing absorption features from water. And this was really interesting in that maybe at these higher temperatures, there's less condensation happening. There's also maybe a step function around 800 Kelvin where the dominant carrier of carbon moves from methane to CO. So methane is really good at making haze, CO is less good. And so perhaps we're seeing a step function at around 800 Kelvin rather than a linear trend. More recently, there was a really exciting result for a much cooler planet. This is K2-18b, which is actually in the habitable zone of its host star. And this planet has a beautiful absorption feature that has come into a bit of question more recently. So it was initially thought that this was a water absorption feature. Then there were some new studies that showed maybe it was a feature from methane instead, which may be the dominant absorber at these low temperatures. And finally, just last week, there was a new result from Tom Barclay et al. Showing that maybe the feature could even be due to contamination from water in star spots for the host star. So I think this is still a developing case, but it did motivate a really interesting lab study about what the properties of atmospheric hazes might be at different temperatures. So this is work from Xinting Yu. Sorry, that's a typo there. That should be a Y. And she measured the surface energy of haze particles in the lab over a range of temperatures. And she found that at these lower temperatures, the surface energies are actually higher, which means that haze particles will efficiently grow and rain out. Whereas there's a sweet spot for haze formation in this kind of 400 to 600 Kelvin range, where haze particles don't grow as quickly. And that means that they linger in the upper atmosphere, making perhaps very, very, very hazy planets like GJ1214b. So I think this is a really interesting demonstration of how much synergy there is with lab science and the interpretation of exoplanet atmosphere observations. And I hope this will motivate new data in here to see whether this trend really holds true for a larger sample of planets. Okay. So the last thing I want to talk about is rocky planets, and these are for some people the most interesting. I like planets of all sizes, but rocky planets are fun, particularly because we're finally pushing to characterize them in more detail. So we know from the solar system already that we should expect a diversity of atmospheric properties. Of our 4 terrestrial planets, 2 of them have thick atmospheres, Venus and Earth, and 2 of them do not, that's Mercury and Mars. The factors that shape whether your planet has an atmosphere or not, if it's a rocky planet, are very complicated and numerous. So it depends on what the composition of the rock is and how much material is outgassed, how the planet cools over time, how the atmosphere erodes or evaporates, particularly in the early lifetime of the planet, whether there were giant impacts that could blast off the atmosphere. So there's many, many, many factors. And we also know that the planets of the solar system are in some sense not representative because we have a sun-like host star, the sun, whereas most of the rocky planets in the galaxy actually orbit M dwarfs, which may have had very different evolutionary histories thanks to their bright, long pre-main sequence phase where they're very bright in the UV and can easily evaporate a substantial atmosphere from the planets. So rocky planets are small, and so it's challenging to observe them, but we've made some progress recently by looking at hot ones. And the idea here is that if you want to know the 0th order question, does the planet have an atmosphere or does it not, you can observe a thermal phase curve to search for signatures of heat circulation by a thick atmosphere. And the idea here is that if you have a thick atmosphere on the planet, it efficiently redistributes heat from the day side to the night side, and so it lowers the temperature contrast between the two hemispheres. On the other hand, if the planet has no atmosphere at all, you would expect a maximum temperature difference between the day side and the night side. So the amplitude of the phase curve is a really good diagnostic of whether an atmosphere is present. And recently, TESS discovered the Rocky Planet Lhs 3844b, and this is the first rocky planet that is accessible for this type of observation. In some sense, it's representative of the broader population of rocky planets around M dwarfs. It has its host star is about 20% the radius of the sun. The radius of the planet is 30% larger than the Earth. But what makes this planet special is that its orbital period is only 11 hours. And so the equilibrium temperature is high enough that the thermal emission from the planet is detectable. And indeed, I went after this with the Spitzer Space Telescope. Fortunately, this was the last year of Spitzer's life, so we just caught it. This is the thermal phase curve of the planet. You can see the eclipse right here at orbital phase 0.5, and then this decrease in flux here as the planet's day side rotates out of view. And what we're seeing here is the maximum possible temperature contrast between the two hemispheres. So the night side is consistent with 0 Kelvin. The day side, the substellar point, is hotter than 1000 Kelvin. And our analysis of this phase curve showed that surface pressures greater than 10 bars are very confidently ruled out. The more CO2 you put in the atmosphere, the lower the surface pressure has to be. We also found that less massive atmospheres are unstable over the lifetime of the planet. You'd expect them to erode by stellar wind. And what we think is that most likely we're looking at the surface of a rocky planet, and the albedo has to be very low, less than about 0.2. And that's most consistent with a very dark rock analogous to a basalt that you might see on the surface of Mercury or the lunar mare. And so that's pretty speculative, but it's a fun thing to think about, that we're really looking at a rocky surface of another planet. Okay, so this is my last slide. We have an enormous amount of data to look forward to from JWST for rocky planets. There are already more than 10 rocky planets scheduled to be observed during cycle 1. Here's a simulated data set for what type of spectra we might expect. This is simulated thermal emission spectra of TRAPPIST-1b with the MIRI instrument, and you can see that these different atmosphere models that are dominated by water or methane or CO2 have very different spectral features. And so not only will we be able to tell what types, whether an atmosphere is present at all, but also we'll start to explore the first diversity of what the atmospheres are made out of. So I'd like to leave at least a little bit of time for questions. So I'll wrap up here, and thank you again for your time.